Friction is a force between two surfaces that actually resists motion. We talked about, if you slide your feet, if you're on a carpet and you're walking around sliding your feet, there's quite a bit of friction. If you're on a sheet of ice, there's much less friction resisting your force. Okay? And that's what something is slippery. What slippery means is very low friction. Okay? And so friction resists movement. Okay?
So, what you were talking about, like, last class with the glue, and if it were in, like, a no friction place, but there isn't? If we, like, ran and then, like, slid, would we just keep on sliding forever?
So if there was a friction-free surface, yes. If you, not even if you ran, if you just did this.
Is that flying?
I mean, the only reason you stop moving is because there's friction between your foot and the ground. But if there were no force of friction, then Newton's first law, the law of inertia, says you should continue moving forever.
But that would be so scary.
Okay? So also, what Newton's law says is an object that is at rest will stay at rest unless acted upon by an outside force. An object in motion will stay in motion unless acted on by an outside force. And this is why, if you, in space, for example, when an astronaut has to do a spacewalk and go outside of the space shuttle or the space station, they're always tethered to it. Because in space, there's basically zero gravity where they are. But there's also very little air resistance, or there's basically space is almost a vacuum. And so if they push off of the space station, they would just begin floating away, and they'd basically be moving almost forever. Because there's nothing to stop them from moving. Because of the law of inertia. Once they go into motion, there's no force that's going to stop them from moving. And therefore, they'll float away forever. All right. Some examples here. So, if you ever seen that tablecloth trick, where somebody takes a tablecloth. Let's see. Can we recreate this? Give me a
Glue stick.
Oh, that's too much. All right. So I don't know if this will. All right. So this object is currently at rest, and hopefully will stay at rest.
Oh! Very good.
Okay.
Very good.
Now, what if I done this same experiment using a piece of carpet? Would this experiment work?
No.
No, because there would be much greater force of friction between the carpet and this. Between the paper and the water, there's relatively little friction, so I can whip it out of there fairly quickly. No. All right. It may work. It just depends on the forces applied and the amount of friction. All right, that's Newton's first law. The objects on the table are at rest, and therefore they tend to stay at rest. Now, you are exerting some force as you whip out the tablecloth, but if that force is resists that friction, then the objects are going to stay at rest. The other thing, an object in motion. Okay? If you've ever were riding your skateboard down the street and then you hit like a rock or you hit a curb, what happens to you? You go flying. You're riding your bike and all of a sudden somebody sticks a stick in your spokes. What happens to you?
Oh my God.
You go flying. This is because of Newton's first law. As you're riding your bike, you're in motion. You will stay in motion unless acted upon by an outside force. So when your bike stops, you are still in motion. You continue over the handlebars and go flying. It's why when somebody slams on the brakes in the car, you go forward because you're in motion. The car stops, but you continue forward. Because of the law of inertia, and the seatbelt is what holds you back. Victoria?
Can I tell a really quick
Quickly.
story? Okay. So my friend was having I think it was her sister's birthday party, and we're going down Westminster on scooters.
Mm-hmm.
And it's like it's a hill, it's a street, but it's kind of like a hill. And I said, no, I'm not going to do that because I'm just going to fall off or a car's going to hit me. And so, but then finally I was convinced to go down it. In the car, I could see a car coming up. And so I was riding with Abby Friedel. And I said, Abby, I'm going to jump off because the car was going to hit us and you can't stop. And so I jumped off, and then the car turned the other way.
And then you're,
When I jumped off, I fell. Like apparently Abby said like I flew like really high in the air.
yeah, again, if you jump off of something that's moving, the thing is, if it's moving a certain rate of speed and you jump off, you're continue moving, and so therefore, if your legs can't keep up once you jump off, then you go flying.
Yeah.
All right, I can't hear a story about every time everybody fell though. Yes, question.
How come if you're riding your bike and you use the back of
If you what?
use the back?
Oh yeah.
Because the force of that is sort of slowing down your body. If you stay attached to that bike, okay, then the problem when you use the front brake is that the front stops, but the back continues, and so therefore that force sort of brings you over the handlebar.
I've done that before.
Because you're slowing down the front of the bike.
Okay, so like when you like check the questions tomorrow, are we gonna go over that?
Possibly.
Okay.
All right, so this guy goes flying out of the car because of inertia. Mr. Akira on his motorcycle. Again, another example.
Wait, you didn't see the brick wall?
That's a nice car.
He's like a ninja.
Okay, that does not happen.
That happens.
Okay. Ladder goes flying off the car.
Where did you get these gifts?
I don't know. All right. Newton's second law then. So the first law has to do with the object that's being active, that's at rest or in motion, continues that way. Newton's second law says that if you do have an object, okay, the greater the mass of the object, the more force that needs to be applied to accelerate it, which is sort of common sense. Okay? If you have just a skateboard and you push on it with your finger, it's going to start moving. If you have a bike, you're going to have to exert more force. If it's a car, then you're going to have to exert much more force. Okay? The more mass of the object, the more force it will take to accelerate that. So what we have with the Newton's second law is a formula. Force equals mass times acceleration. Okay? And so obviously, if we have two carts, one's filled with stuff and one is not, which one's going to take more force? Obviously, it's going to be the one that's filled up. And the more force you apply, the greater it's going to accelerate. So if you push the cart harder, it's going to accelerate more quickly. If you don't push with as much force, it's going to accelerate more slowly. All right. Here's my Star Wars joke.
I don't get it. I never seen Star Wars.
Force equals mass times acceleration.
Oh, that you that people and you're having seats.
I know, that's sad to say. All right, so we use Newton's second law to solve problems often. Here's a couple examples. Okay? So Mike's car has a mass of 100 kilograms, and it's out of gas, and he's trying to push it to a gas station. So if he makes the car go 0.5 meters per second squared, that's how much he causes the car to accelerate. You can use Newton's law to determine the force that he applied. Okay, force equals mass times acceleration. The mass of the car is 1,000 kilograms. The acceleration is 0.05 meters per second squared. So if you solve that problem, you'll find that the force he applied was 50 kilograms times meters per second squared. And we have an abbreviation for that unit. The units for force are often used in newtons. N is for newtons. A newton is 1 kilogram times meter per second squared. So Bob has a van. It's 2,000 kilograms. It's also out of gas. He's going to make it accelerate 0.05 meters per second squared. Again, how much force would he have to apply?
A lot.
2 times that.
Twice as much. The car is twice as massive. Therefore, you have to apply twice the force to cause it to accelerate.
They just help each other.
Nicholas?
Is the Bob we're talking about Bob the Builder?
No,
Yes.
it's not. That's hippie Bob. All right. Newton's third law. Newton's third law states that every action has an equal and opposite reaction. So every time two objects interact, okay, they exert a force on each other. So when Mr. Akiri punched me, making me have a bloody eye, okay, there was a force that he applied to my eye. Okay? But
Yeah.
my eye also applied a similar force to his hand. Okay? And this is often comes into play if you think about a rocket, okay? As explosive gases come streaming out of one end of a jet, okay, that causes an opposite action which moves the plane or moves the rocket forward. Okay? Or if you are, here's some more examples. If you're in a canoe, and you go to step out, okay, as you jump off of it, you are pushing against the canoe to propel yourself forward, but also you exert an equal force in the opposite direction, which causes a canoe to move the opposite way. If you think about it, if you're standing on some sort of rolling device with wheels,
This thing is dangerous.
such as this.
Why do you have that?
I don't like that.
So if I stand on this such object, if I push against this desk, I'm pushing against the desk with a certain force, but it also exerts a force against me, the same amount. No.
Those things are all jump off, jump off.
I'm standing on it though.
Jump off.
I'm a rebel.
At the bottom,
A loner.
it says you're not allowed to stand on that.
You wouldn't want to get mixed up with a guy like me. You know what that quote's from?
Lone Ranger.
No.
I want to see that.
It's like an old movie, right?
Some
old movie.
It's Pee-wee's Big Adventure. Anyway, so Bob is tired of pushing his van to the gas station, so he's going to make it a little bit easier. He's going to put rollerblades on and do it. Good idea?
No.
No, bad idea. Because the force that he exerts is going to push him backwards. Okay? So he's going to push on that van with a certain force. Let's say it's 100 newtons. But that van is going to push back on him with the same force, causing him to move backwards. Okay? Yes.
You should check if the parking brakes are on, because
You
if
should.
they are, then that's even more.
Well, what's the question? What's different between him pushing the van before and him pushing the van with rollerblades? What has changed? Friction has changed. Between his sneakers and ground, there's quite a bit of friction that's going to prevent him from moving. But wheels, their purpose is to reduce friction. That's why you could slide all over on this thing, whereas if I was just standing on the ground, I couldn't.
Actually, could if you have water.
This law also describes why there's like kickback on a gun. If you fire a gun, if you ever fired a gun and you see in the movies, you don't just like go bam and then your arm stays still. There's a kickback. And that kickback is caused by the opposite force. There's a large force causing the bullet to leave that gun at a high rate of speed. That opposite force is what pushes against a person's arm.
One time when my dad was firing a shotgun, he broke his collarbone because if he was holding it onto the sight
Oh, yeah.
recoiled.
Yeah.
Ow.
All right. So, if we summarize Newton's laws, okay? Newton's first law.
Inertia.
Okay, the law of inertia. Okay, an object at rest will stay at rest. An object in motion stays in motion. For example, your book, your binders sitting on your table, they're at rest and they're staying at rest. Is there any force on them right now? Is there a force on your books on your desk?
There is yes.
Yes, the force of gravity. So why aren't they moving?
Because there's something holding it down.
Because the desk is exerting an equal force to gravity, holding them in place. All right. Law 2. The more mass an object has, the more force it will take to move it, to accelerate it. Force equals mass times acceleration, and it takes a lot more force to push a filled up wheelbarrow than it would to push an empty wheelbarrow. Law number 3. Every action has an equal and opposite reaction. If you push a wall, it pushes you back. Okay? If you punch a wall, you exert a force on that wall, but it also exerts the opposite force on your hand, causing it to hurt.
So when you say if you had two barrels and one was empty and one was filled with water, what does the one with water get down there first?
If you're talking about rolling down a hill,
Yeah.
no. They would arrive at the same time. Dropping two objects. So if you drop, if I have a plastic hollow ball, I drop, and I have a bowling ball of the exact same size, and I drop them both. Which one hits the ground first?
The volleyball.
They hit at the same time.
Same time.
Wait.
Heavier objects do not fall faster.
Well, like a car and like a feather.
Now, what's the difference? So if I have a feather and a bowling ball, the difference is in air resistance. That's why it's important that the two balls are the exact same size, because then they have the exact same air resistance. Okay? There's a video later on in your notes that shows somebody standing on the moon dropping a feather and a hammer at the same time. And you'll see that on the moon, because there's very little air resistance, they drop at the same rate.
Wait, how would they drop it? I don't even know.
All right. Momentum. Let's talk about momentum and we'll move on. So momentum is a term that talks about how difficult it is to move an object or to stop an object. Okay? The formula for momentum, it's the mass times the velocity. Okay? And so momentum, you can calculate it. If we have a barrel that's rolling at 50 kilograms, it's rolling 10 meters per second. Okay? Its momentum would be 50 times 10, which would be 500 kilograms times meters per second. Okay? So this has to do, which would you rather get hit by? Which one is going to hurt more? A 200 kilogram linebacker that hits you at a speed of 2 meters per second, or a 100 kilogram safety running at you 4 meters per second? Same, the same momentum.
It's gonna hurt though.
Okay? Could a rolling marble and a rolling bowling ball ever have the same momentum?
Yes.
No.
Yes.
No? Yes.
No.
Yes. When?
Wait,
When
they first start.
No.
Bowling ball is going slower than the marble.
When the bowling ball is going very slowly and the marble is going very quickly. Okay, again, momentum is mass times the speed or velocity. And so yes, they would if the marble was rolling very quickly, or the bowling ball was going very slowly. All right, last one for today. Centripetal force. Centripetal force is the force that's directed towards the center of a circle when an object is swinging around. For example, this person swinging a yo-yo around in a circle, okay? The force that allows the yo-yo to keep spinning around and not go flying forward is called centripetal force. What happens when the string breaks?
It's gonna line.
Yes, it goes flying in what kind of line? A straight line. You know, if you ever whip something around like this and let it go, it just continues straight once you release that centripetal force. There's another type of force, okay, called centrifugal force. And so, another example, if you are in a car and you take a fast turn, or if you ever went on the scrambler thing that spins around, which seat do you not want to be in?
The outside.
The one on the end, because all of the force of those people is pushing outward, okay, on you. Because you're moving a certain direction, and as that thing spins, you tend to stay moving towards the outside, and then you push against your friend. If I think about this bucket,
Is there water in there?
I will put some water in here.
Good.
So if I put some water in this bucket, okay, alright, if I take this bucket, can I swing it
Yes.
around my head?
Don't let go of it.
So what force is my arm applying to it?
Gravity.
Centripetal force. Why does the water not spill out?
No, because there's no water in there.
There is water. I
No.
just put the water in
No,
there.
there's not. Don't show me.
So there's a point.
No, keep on doing it. Like,
So what if I do it more slowly? You can exactly feel sort of when it's gonna. The faster you swing it, because the water as it's moving is pushing against the bottom. It wants to continue straight. Okay, but because that bucket's there, okay, it continues. It stays in the bucket.
What if you do it right?
Yeah, I hear it.
So you just have to trust the laws of physics that you're not going to get wet. Oh, yeah, that was close. All right. Tomorrow I'll tell you one other thing about trusting the laws of physics in this time. Remind me to show you this tomorrow.
Oh, I know what you're gonna do. You're gonna hold it up
All right, don't forget your homework tomorrow.
How do you like that?